Hello! Today we're going to be dealing with nuclear equations of reaction, whereas in the last lesson we were dealing with what we call so-called alpha, beta, gamma decay, or the splitting off of neutrons and protons. Then today our lesson will be about how, for example, the bombardment or the capture of electrons, this is this process that you can see here, or for example, this is a decay process that can be accompanied by the splitting off of different particles as well. For example, it can be the positron particle. Positron is a particle, opposite in charge to electron, but a particle which has the same small mass equal to 0. But besides that, we will see today in the lesson also the question of what particles can be produced during decay. That is, today's lesson is devoted to capture and decay of particles which are formed when elements are exposed to different particles. So let's remind ourselves how we work with these reaction equations. Let's say we are given this nuclear interaction, and the question is what chemical element will be obtained on the right side. In order for us to answer the question, what do we need to know? We have to establish what the sequence number or the charge labeled Z, and what will be the mass of this element or this atomic mass or the mass number is called this value. So let's remember how we do it. So first, let's see what we have on top here. Let's determine how we get this value A and see what we have on top for calcium. We have 40. And then we have electron mass, but it's 0. And it turns out that this is all equal to our mass of the unknown element. Well, from here it's quite clear that we have A will, in this case, be equal to 40. Now the next thing we have to do is to determine what we're going to have. We have a charge that is the letter Z, then we'll see that we have 20 on the left-hand side. And then the electron has a charge of -1. And then by the rules of math, which is our Z, we can establish that our Z will be 19 in this case. Now we have to determine what chemical element this is. But since it is the ordinal number of the element that is the main thing for us, because the mass of the isotopes can be different, we can come to a conclusion as to what this chemical element is. So, number 19 is the element, potassium, and it's number 19, and it has a mass of 40. This is one of the isotopes that this chemical element has. What remains is to write the equation of the nuclear reaction. So we've taken calcium, number 20, and mass 40, subjected it to electron capture -1, 0, and the unknown element on the right-hand side is potassium 19 of mass 40. That answers the question of what is the unknown element. We move on to the second case, and in this case there is a decay, and the particle that goes away is a positron. So we work in exactly the same way. We have let's find the mass of this unknown element. To do that, we have 15 on the left side. The positron has a mass of 0 on the right side. And then we have the atomic mass of our unknown element. According to the rule that governs this calculation, called the Soddy-Fajans rule, it turns out that we have for this unknown element, the mass will remain the same, and it will be equal to 15. Now we have to determine what our charge will be. On the left side, it's equal to 8. On the right side, it will be +1, well, or it's 1, 1 plus Z. In this case, we're going to have Z equal to 7. and we've got an element whose number and mass are known to us. But since the main thing, again, I'll emphasize, is its number, we determine what element it is. And this element is nitrogen because it has the number 7 and it has an isotope with a mass of 15. Now we just need to write our equation. So oxygen, 815, is converted by positron decay into the element nitrogen, which has the number 7 and mass 15. Okay, well, let's see what other decays there are. The suggestion here is to find what element the unknown element would be if alpha decay occurs. Well, in order to do that, we use the same rule. So the first way to do this is to establish what the mass will be. So on the left side we have 31. On the right hand side we have 4 plus the unknown atomic mass of the element. Then in this case we can easily calculate that we will have a mass of this element of 27. Now we need to establish what our charge will be. Now, to do that we have 15, which is the number we see on the left hand side of phosphorus. And on the right hand side of the alpha particle we have 2. And in this case we have the charge of this element, that is its number, will be unknown. But since we must have a total of 15, we can easily conclude from this that we have this element with the number 13. And since the 13th number is the most important number for identifying our unknown element, we have to write down the equation. So phosphorus number 15. 31 in the alpha decay. It's turned into the element aluminum. And it's number 13 and mass 27. At the same time, when determining which decays exist, there are additional rules that we usually use in order to quickly identify which element will be obtained. Well, I'll give you the last example of how to do it. Look, with alpha decay, the element goes back 2 cells. If there was bombardment by alpha particles, then we get an element moving 2 cells forward into the next element. So we would have an element moving 2 ordinal numbers forward. If it was positronic, let's say, decay, notice we get an element moving 1 cell forward. And if it were a positron impact, that is capture of a positron, then in this case we would have an element shifted 1 cell forward. If there is, for example, an electron capture, then the element moves 1 cell backwards in the periodic table. So the element goes 1 number backwards. And if on the contrary an electron is captured, that is beta decay with the help of electrons takes place, then the element would move on the contrary 1 cell forward. This is how you can predict what the results of nuclear processes will be. And at the next lesson we will try to deal with more complex nuclear transformations when the participants of the process both on the left and on the right sides will be not 1 or, for example, 2, but perhaps there will be even several of them. We will also discuss such nuclear reactions. Goodbye.